Hello, I am William J. Hale, an independent journalist with interests in science. Today I am inviting two of the most eminent contemporary scientists to discuss nuclear fission and fusion. It is with great pleasure that I am introducing songwriter and nuclear physicist Dr. Stevie Wonders.
Hello there.
So, Dr. Wonders, you specialize in fission. What exactly is fission, and when was it discovered?
The discovery of fission is attributed to Enrico Fermi, an Italian physicist. He showed that through bombarding certain elements with neutrons, these elements would in turn transform into new elements. Nuclear fission is when the nucleus of an atom splits apart into smaller parts. In this process, free neutrons and gamma rays are produced, in turn releasing large amounts of energy.
So here we have an example of nuclear fission, and this is actually one of the first examples which were created in a lab environment. So a uranium-235 atom is bombarded with a neutron, which in turn creates a uranium-236 atom, which enters into an excited state, dividing into a krypton atom and a barium atom, releasing 3 free neutrons and high amounts of energy at the same time. What scientists noticed was that the spare neutrons produced in this fission reaction could cause other samples of the element to undergo fission as well, prompting a chain reaction in which even more energy is accumulated. This chain reaction led to the idea of nuclear energy being used in war.
So, Dr. Wonders, a well-known example of fission is the atomic bomb. Developed during World War II, how was this devastating weapon different from the conventional weapons of the time?
Well, conventional weapons use chemical reactions, whereas nuclear weapons use nuclear energy. The main difference is that the yield of nuclear weapons is exponentially greater than that of conventional weaponry. The atomic bomb makes use of the chain reaction in order to produce an explosion. For this reaction to occur, there must be a nuclear fuel. This nuclear fuel is the element which is used up in the process of the chain reaction. In order to increase the efficiency of this reaction, a dense material known as a tamper surrounds the reaction. When the reaction begins, the heat and energy produced causes the tamper to exert pressure to the core, slowing its expansion and increasing the efficiency of the chain reaction. For nuclear chain reaction to occur successfully, there has to be a certain concentration of the nuclear fuel. This is known as the critical mass. In order to prevent premature explosion, however, the fuel is separated into subcritical masses which are not capable of sustaining a nuclear reaction. However, these subcritical masses have to be recombined into a supercritical mass in order to sustain the nuclear reaction necessary to produce the bomb's explosion. And bomb designers came up with 2 different solutions to this problem.
So, what were these 2 different solutions?
The first solution, used in the Little Boy bomb that was dropped on Hiroshima, was a gun design. In this situation, there is a sphere of subcritical uranium at the end of a chamber and a hollow uranium bullet on the other side. The gun is controlled by a barometric pressure sensor which detonates the explosives at the proper altitude, which fires the hollow uranium bullet through the chamber. This combines with uranium sphere to produce supercritical mass, causing the neutron generator to fire neutrons and initiate the reaction. The second solution they developed was used in the Fat Man bomb dropped on Nagasaki. It's an implosion type. A plutonium-239 core is surrounded by a tamper of uranium-235 and high explosives. When the explosives are detonated, the shockwave produced compresses the core and begins a fission reaction.
A current common use for nuclear energy is the generation of electricity in nuclear power plants. How do these go about generating energy?
Nuclear power is not nearly as extravagant as you would expect. This is the basic process. Uranium-235 is collected in small rods, which are put together in bundles and submerged in heavy water inside of a pressure vessel, with the water cooling the uranium, which would otherwise overheat. Control rods are inserted into these bundles to control the rate of the nuclear reaction. This reaction is used to heat the water, which turns into steam. This steam drives a turbine, which spins a generator and produces electrical power. It's as simple as that.
What are the pros and cons of this type of energy?
Well, the first point in terms of its benefits is that it is far more efficient both in terms of its environmental effects and energy yield than any other contemporary alternatives, such as fossil fuels. A pellet of uranium, weighing approximately 6 grams, has the same energy yield as a metric ton of coal. Also, nuclear energy avoids the pitfalls of fluctuating prices which face things like oil, as well as significantly reducing the amounts of CO2 produced in the process. However, this situation is far from ideal. The mining and enrichment of uranium is a very environmentally destructive process, and the transportation and storage of uranium poses serious contamination risks. There are also concerns about the safety of nuclear reactors themselves, with disasters like Chernobyl causing widespread damage when the nuclear reactor safety system was compromised. Also, nuclear power plants produce high-level nuclear waste through used nuclear fuel, as well as low-level radioactive waste through radiated equipment. And, although radioactive materials do eventually decay to safe radioactive levels, this process may take thousands of years, meaning that the waste has to be continuously regulated and cannot be simply thrown away.
Thank you for your time, Stevie.
Thank you for having me. Would you like to hear a joke before I go?
Why not?
What do you call a group of nuclear engineers doing sit-ups and crunches?
What?
The core development team.
Oh, that was a good one. Well, we will return to talk to Dr. Barnes about fusion after this short break.
Older blocker body wash is so powerful it can block BO for 16 hours. It's so powerful it can turn off the sun. But then it gets too cold, so it makes another sun. Double sun power! Power!
Welcome back, viewers. I have Dr. Barnes here, who will be talking with us about nuclear fusion. So, Dr. Barnes, some of our viewers may be unfamiliar with the concept of nuclear fusion. What exactly do scientists mean when they talk about this subject?
Well, to start off, fusion was discovered by an Austrian named Lisa Meitner, who worked with German chemists Otto Hahn and Fritz Strassmann in 1938. Fusion is the process where two nuclei form to create a heavier and more complex nuclei.
This is a picture describing how two isotopes of hydrogen, known as deuterium and tritium, undergo fusion. First, they are heated to 100 million degrees Kelvin. At these temperatures, the atoms enter the fourth state of matter known as plasma. Plasma is a state in which all atoms shed their electrons and exist only as nuclei. Second, they are compressed to the point where they fuse and create a helium atom. Since helium atoms require only 2 neutrons and 2 protons, the third neutron is displaced. The energy required to displace this neutron is so great that when the neutron is displaced, there is a massive release of energy along with the neutron and the helium atom. This process carries with it 2 important requirements in order for fusion to occur.
Well then, what are the requirements for fusion?
So the first of the two is high temperatures. The high temperature gives the hydrogen atoms enough energy to overcome the electrical repulsion between protons. Fusion requires temperatures of around 100 million Kelvin. The Sun achieves these temperatures by its large mass and force of gravity compressing the mass of the core. We must use energy from microwaves, lasers, and ion particles to achieve these temperatures. The second is pressure. High pressure is critical. The pressure squeezes the hydrogen atoms together. They must be within 1 × 10 to the negative 15th meters of each other to fuse. With current technology, we can only achieve these temperatures and pressures necessary to make deuterium-tritium reaction, otherwise known as DT fusion, possible. Deuterium-deuterium fusion requires higher temperatures that may be possible in the future. Ultimately, deuterium-deuterium fusion will be better because it is easier to extract deuterium from salt water than to make tritium from lithium. Also, deuterium is not radioactive, and deuterium-deuterium reactions will yield more energy.
Now, you said that fusion would be difficult, but is it even possible to achieve this process on Earth?
Well, thankfully, yes it is. There are 2 ways to achieve the temperatures and pressures necessary for hydrogen fusion to take place. The first is magnetic confinement, which uses magnetic and electric fields to heat and squeeze the hydrogen plasma. The fusion reactor will heat a stream of deuterium and tritium fuel to form a high-pressure plasma. It will squeeze the plasma using powerful magnets so the fusion can take place. The power needed to start the fusion reaction will be only about 70 megawatts, but the power yield from the reaction will be about 500 megawatts. Eventually, there will be sustained fusion reaction. The second step, the metal containment wall outside the plasma reaction chamber will absorb high-energy neutrons. Since neutron charges are neutral, the magnetic fields do not affect them. This allows the neutrons to pass through the magnetic field and absorb into the metal containment wall. This wall then becomes white hot, which will heat the surrounding water into steam, and this steam is used to power a basic turbine.
So, earlier you mentioned a second method, and you said it was inertial confinement?
Yes.
What is inertial confinement?
Inertial confinement uses laser beams or ion beams to squeeze and heat the hydrogen plasma. So in this case, 192 laser beams will focus on a single point of deuterium-tritium encased in a small plastic cylinder. The power from the lasers, at 1.8 million joules, will heat the cylinder and generate X-rays. The heat and radiation will convert the pellet into plasma and compress it until fusion occurs. The fusion reaction will be short-lived, however, about 1/1,000,000th of a second, but the yield is 50 to 100 times more than the energy that is needed to initiate the fusion reaction. The problem with the reaction is having sustained reaction and injecting fuel quickly enough.
So before you came here, obviously I researched fusion a little bit, and as I was searching, I've heard something, well, I saw something called cold fusion. What exactly would cold fusion be, and is it possible to achieve this?
Well, to start off, it is not possible. The idea of cold fusion is to produce fusion reaction without needing to be heated to 100 million degrees Kelvin. But mainstream science has rejected this idea because of the very basics of physics dictate that if you have energy, there is heat, or if you have heat, there is energy. These two very basic principles are interchangeable. One cannot exist without the other. It's like a sandwich without bread. It's like a car without wheels. It's simply not possible.
Well, Dr. Barnes, I think it's about time to wrap up our interview. But I'd like to ask you one more question.
Yes?
What do you see in the future of nuclear fusion?
It's a very bright future. In the future of nuclear fission can provide a safe, clean energy source for future generations with several advantages over current fission reactors. Firstly, there's an abundant fuel supply. Deuterium can be readily extracted from seawater, and excess of tritium can be made from fusion reactor itself, from lithium, which is readily available in the Earth's crust. It's safe. The amounts of fuel used for fusion are small compared to fission reactors, so there's no uncontrolled release of energy. It just doesn't occur. There's no combustion, and there's no nuclear waste. Fusion reactors will produce no high-level nuclear waste like their fission counterparts. When we're successful, we will have an energy source that is inexhaustible. I'll put it to you this way. A gallon of water has the energy content of 300 gallons of gasoline.
Thank you for your time, Dr. Barnes. It was nice discussing your field of study. This wraps up the show tonight, everyone. I hope this was an enlightening experience for you all. And good night.
Hello, I am Adam Peterman, and this is an independent journalist report with an interest in science. Today we are inviting two of the most eminent contemporary scientists to discuss nuclear fusion and nuclear fission. It is with great moderate pleasure that I now introduce... I told you that wouldn't work!
Great moderate. So, Dr. Barnes, many of our viewers may be unfamiliar with the concept of fusion. What exactly is meant when scientists talk about nuclear fusion?
Moment.
Come on, Doctor. So, Dr. Barnes, many of our viewers may be unfamiliar with the concept of fusion. What exactly is meant when scientists...
New lenses.
Alright, here, I'll try again.